video, I'd like to give an overview of the cardiovascular system. Um, so basically describing how the heart and the two vascular circuits I have listed up at the top here are linked. And really, this is a very simplistic, very schematic drawing, but it shows you how the heart is sort of the hub of these two circuits, right? The pulmonary circuit on this side and the systemic circuit on this side. And again, really schematic here, just trying to show you the layout and why we're sending blood flow to these through these two circuits, and then how the heart is in the middle of these two circuits and aids blood flow through them. So we can think of the heart as sort of the hub of this. Let's start here in the middle, talking about the heart. I've got this sort of schematic Valentine's heart in the background here. And then inside of it, I've shown you the four chambers of the heart, right? And so the four chambers are the left and right atria up here, and then the left and right ventricles, the larger more dramatic pressure generating chambers. And so first off, let's start by saying that the atria serve as performance enhancers for the ventricles, right? Their function is to top off the filling of the ventricles from the blood that returns to them. You can see that with these arrows coming back, carrying blood flow into the left and right atrium. And keep in mind, this is happening simultaneously. Both halves of the heart are filling and pumping at the same time. And you really want to think of the heart as not one pump, but two, because each half of the heart is sort of serving as a pressure generating pump for its own circuit, right? So I really want to emphasize a septum, the wall that separates these two pumps. They definitely work as a unit. They do pump together, but we want to think of them, at least in terms of understanding the system, that the right heart is pumping blood, as you can see here, follow this arrow. And I'm going to use blue to emphasize this arrow. Sorry, it's a little messy. There we go. Right? The right heart is pumping blood to the systemic circuit. The blood's going to return to the left heart, and then that heart is going to pump blood to the systemic circuit, which comes back to the right, and over we go. So it's sort of this figure eight looping, if you will, through those two circuits with the heart in between. Okay, but let's follow the what's happening and why it's happening by starting, picking a spot and following the blood. And so we've got number one over here, right here. Right, we're going to start here, and this is arbitrary. We're just sort of picking a spot to sort of, start examining where the blood's going to go from A to B to C, or 1 to 2 to 3. So we've got blood leaving the right atrium through the AV valve, the atrioventricular valve, into the right ventricle. The right ventricle will then contract, and the atria contract together, by the way, and the ventricles contract together, but they're offset in time by a little bit. We'll talk about that later on. But the ventricle, so the atria helps fill the ventricle. Then the ventricle contracts and pushes blood out. Really, the function of the ventricles to generate the pressure that pushes blood out into the circuit, right? And so if we sort of highlight our pathway here, blood's going to leave the right heart, and it's going to travel to the lungs, where it's going to enter the capillaries that surround the alveolus. Let me highlight the alveolus for you here. Right, this alveolus is the air-filled sac, which is where gases are exchanged to sort of regain homeostasis of the blood gases, right? And so what we have here is the blue indicating, in this case, right, blue equals deoxygenated blood. Now, it's partially deoxygenated blood. It doesn't have no oxygen in it. It's just partially deoxygenated. And in fact, it's actually more of a maroon, but it does change color when it becomes deoxygenated versus oxygenated. And which is why in anatomy, when you learn the blood vessels, they're often shown as red and blue. Right? The red and the blue refers not to artery or vein, but to oxygenated or deoxygenated blood, or at least it usually does, right, on those figures. And so another key point here is that arteries carry blood away from the heart, right? We've got our pulmonary arteries here listed, right? They're carrying blood that is going to be high in carbon dioxide and low in oxygen. We already talked about this, low oxygen, right? Again, when we get through the circuit, this will make more sense. We get to the air sacs at the lung, and what's going to happen is we're going to pick up oxygen by diffusion. We're also going to lose carbon dioxide to that air, and the blood is going to become more reddish, right? It's going to become more bright reddish as it leaves those alveolar surfaces, right? And that blood's going to come back into the heart over here, right? As now oxygenated, bright red blood. And note, it's carried in veins. Veins carry blood back to the heart. So we had arteries carrying blood away from the heart. We had capillaries right here, right? Capillaries where our exchange occurs. That's where diffusion can occur because they're very thin-walled. Then the blood coalesces into a smaller number of larger veins, which are, and again, by definition, veins are carrying blood back to the heart, right? But notice now, right, we're going back to the heart, and we're going to enter the left side of the heart, right? We left the right side to go to the lungs to pick up oxygen. Now we're coming to the left side of the heart, right? Our oxygenated blood is going to be passing through the left atrium. The atrium is going to help fill the ventricle. Then the ventricle is going to contract very hard, and it's going to push blood, this oxygenated blood, off into this what's known as the systemic circuit. Right? The systemic circuit carries blood everywhere except the lungs, and actually even a little bit of a portion of the lungs that doesn't get oxygen at the alveoli. But essentially the non-lung, non-gas transport areas of the lung. Everything else, your brain, your organs other than your lungs, your muscles, your skin, right? All of that is going to be perfused by the systemic side. And so here we come with this oxygenated blood, right? Coming into the capillary bed, right? We've got our systemic capillaries over here. Right? Systemic tissues where we have a capillary bed. And notice, now let's label these guys. Here are the cells of this particular tissue, whatever it is, liver tissue, muscle tissue, brain tissue, doesn't matter, right? And guess what? These cells are using oxygen. We've got some in between the capillaries here, right? And they're using oxygen, which means oxygen is going to diffuse out of the blood and into this tissue toward the cells. And carbon dioxide is going to diffuse just the exact opposite direction, right? So now the blood leaving this capillary bed will have lost oxygen, which means it's going to become more bluish. It will have gained carbon dioxide, right? So we have to go back to blue, right? Becoming more bluish as we exchange our gases here, and here comes this bluish deoxygenated blood back to the heart to be pressurized and sent to, guess where? Back to the lungs for reoxygenation, back to the left heart for pressurization to the systemic circuit, right, where it becomes deoxygenated, and so on and so forth. And these circuits only take about 1 minute, so this blood's moving very rapidly at rest at a volume of 4 to 5 liters per minute, so rapidly perfusing all of our tissues and making sure they remain well oxygenated and homeostatic about a lot of other things like carbon dioxide and pH and so on. Another thing to point out about these circuits, well, the pumps especially, but the two circuits, let me start with the circuits. The two circuits, right? These circuits are not the same size. I got them here as two sort of equal sides of a figure eight. But the pulmonary circuit is just the lungs. The systemic circuit is all the way to your big toes, right? And so the point here is that the systemic circuit has a lot greater length. It's got more tissues to perfuse. Because of that, and there's some, some key factors we can talk about, but you can imagine that because of that, there's greater resistance to blood flow in that much larger systemic circuit, right? And so to get blood all the way from your heart all the way to your big toes and back requires greater pressure. And so if we look at the two sides of the heart, they are not remotely equal, right? This is why if we look at, let's see if I can label it here, right? If we look at the wall of the left ventricle, it is very thick, right? The wall of the right ventricle is this nice thin line over here, right? Schematically. But the left ventricle is going to have a much thicker, stronger wall because it has to generate a much higher pressure to push blood through that systemic circuit. In fact, the ventricles make up about 90% of the heart mass. The atria are only about 10%, right? And the left ventricle itself makes up about 70 to 75% of the heart mass. It's most of the heart. One of the four chambers is most of the heart mass. And that's because of this really thick wall to generate much higher pressures to overcome the much larger resistance of the systemic circuit, right? So this is the high, oops, wrong pen. This over here would be the high resistance circuit, right? This would be the low resistance circuit, right? Because this is the high resistance circuit, it also has to be the high pressure circuit, right? Remember, you need high pressure to overcome high resistance. We can have much lower pressures on the others in the other circuit. Okay, and that basically lays out the flow pattern through the circuits, as well as reminding us about the oxygenation and deoxygenation of the blood as it traverses those circuits. And of course, the dynamics of the pressure differences and why the heart is not a symmetrical structure, right? Remember that left ventricle is so much bigger than the right ventricle. The two atria look about the same because they're both helping to fill the ventricles when they're not contracting, which means they both are operating under very low pressure. So the two atria are going to look very similar, but the two ventricles do not.